Humanity has practically made crossing billions of miles of empty space look, well, kind of routine. I mean, we've got rovers literally driving across Mars right now. We dropped probes into the clouds of Saturn, and we've snapped these incredible high-resolution photos of Pluto from just a few thousand miles away. But there is one direction we have barely touched: a vertical exit straight up out of the flat planetary plane of our solar system. It sounds so simple, right? Just point the rocket up and go. But as we're going to see in this explainer, physics absolutely refuses to let you do that.
So right off the bat, to understand the core problem here, you have to realize that you are currently trapped. You're moving sideways at 67,000 miles per hour, creating this invisible prison of orbital velocity. And no, that is not a typo. As you sit here right now, you, the Earth, and every single rocket we have ever built are rocketing sideways around the Sun at roughly 30 kilometers per second. This means when a space agency launches a probe, it is never starting from zero. It inherits this immense sideways motion.
Section 1. The orbital velocity prison, escaping 4.6 billion years of momentum.
We've got to confront this inherited sideways speed, because it's the exact reason we can't just point a rocket upward and leave the solar system's flat plane. Normally, we think of this inherited speed as an incredible gift, right? It does most of the heavy lifting to get us to Mars. But the very second you want to move perpendicular to the rest of the planets, that free speed suddenly becomes your absolute worst enemy. Using our existing momentum to hop over to Mars takes very little extra energy, but canceling that speed out just to go vertical requires almost 10 times as much. In astrodynamics, they measure the required energy as delta V, or the change in velocity a spacecraft has to produce completely on its own. To hop over to Mars from Earth's orbit, a spacecraft only needs to generate about 4 kilometers per second of delta V. But to go straight up out of the ecliptic plane, you first have to completely cancel out the 30 kilometers per second you're already traveling sideways, and then add entirely new vertical velocity on top of that.
So the crucial point is this completely counterintuitive reality. Traveling 3.5 billion miles to Pluto is actually cheaper, energetically speaking, than traveling just a few million miles directly above the Sun's North Pole. Think about that for a second. Whenever we launch a rocket, we aren't just fighting gravity. We are fighting 4.6 billion years of sideways orbital momentum, all at once. Because this energy requirement is so staggering, it essentially forms an invisible wall that has kept us effectively locked inside a flat disk.
Section 2. Secrets of solar poles, the engine of space weather. Because this vertical climb is just so punishing, almost no spacecraft has ever made the trip, leaving the poles of our own star as this massive, mostly unseen frontier. Even today, the regions directly above and below our sun are essentially blank spots on our map. We have incredibly detailed maps of Mars. We have stunning close-ups of asteroid collisions, yet the poles of our absolute closest star remain shrouded in mystery. And what's wild is that these unexplored polar regions actually contain the violent engines that dictate the space weather for our entire solar system. The fastest solar winds, they originate at the poles. The sun's intense magnetic field, which famously reverses itself every 11 years, begins its reversal process at the poles. By observing the sun almost entirely from the side, from within our flat planetary disk, we're essentially trying to understand the complex weather of an entire planet by only ever standing at its equator.
Humanity's really slow, difficult progress to actually view these poles only just yielded our very first chaotic pictures last year. In 2025, you look back at the 1990 Ulysses mission, which used a wild slingshot maneuver around Jupiter to bend its trajectory out of the plane. It gave us amazing data on the solar wind for sure, but it relied on 1980s technology and didn't even carry cameras. It really wasn't until the European Space Agency's solar orbiter launched in 2020, gradually tilting its orbit using gravity assists from Venus, that we finally got real pictures. In March 2025, it sent back the very first direct images of the sun's south pole, revealing a magnetically tangled, chaotic landscape that looks absolutely nothing like the smooth sun we normally see from Earth.
Section 3. The shape of our bubble. Seeing the heliosphere from the outside.
Now, getting high above the sun isn't just about the star itself. There's a secondary, equally fascinating reason why astrodynamicists are so desperate to break out of our flat plane. It is the only way to see the true shape of the cosmic bubble we live inside. We need to look back down at our neighborhood to actually understand our place in the galaxy. See, we've been stuck inside this protective structure our entire lives, meaning we have never actually sent a probe high enough to look back and see what it looks like from the outside. This bubble is called the Heliosphere. It holds all the planets, all the comets, and literally every spacecraft humanity has ever launched. By pushing outward against the interstellar medium, it acts as this massive shield, protecting us from deep galactic cosmic rays.
But here's where it gets fun.
While scientists assumed for decades it looked kind of like a comet, a 2020 model using NASA data suggests our heliosphere might actually resemble a deflated croissant. Seriously. For years, the standard textbook image was a classic comet shape with a rounded front and a long, sweeping tail trailing behind it in the galactic wind. But researchers at Boston University completely upended that assumption, playfully but very seriously, proposing a structure with a curved central bulge and two short jets with no long tail at all.
Since Voyager only crossed the heliopause sideways, and newer missions like NASA's IMAP are still refining data from the inside, a vertical escape is literally the only definitive way to look down and see our neighborhood's real form. Voyager's sideways exit was incredibly useful, don't get me wrong, but it was limited, and upcoming missions are still trapped inside the bubble. To definitively prove whether we live inside a comet or a cosmic croissant, we simply have to get a camera high above the ecliptic plane.
Section 4. Falling down to climb up, the astrodynamic solutions. So how do we do it? To finally break out of this sideways orbital prison without needing impossible amounts of rocket fuel, astrodynamicists basically had to hack the physics. We can't just build a bigger, standard rocket. The fuel weight required to cancel Earth's orbital motion is just fundamentally prohibitive. The first solution is the solar Oberth maneuver. It's this brilliant 1929 concept showing that to climb, you must first fall violently inward to convert a deep gravity well into a massive kinetic slingshot. Instead of pointing up, you deliberately drop your spacecraft directly toward the sun. As it falls into that massive gravity well, it accelerates to mind-boggling speeds. We're talking well over 100 kilometers per second. Right at perihelion, the absolute closest approach, you fire your engines. Because of the physics principle Hermann Oberth laid out, burning fuel at high velocity deep inside a gravity well actually multiplies your orbital energy. The violent dive itself becomes your launch pad, providing the sheer kinetic force needed to slingshot straight up.
Now we can contrast that incredibly explosive dive with solar sail concepts, like the proposed solar polar imager, which patiently use the pressure of sunlight on enormous sheets to slowly tilt an orbit over a period of years. Rather than burning heavy rocket fuel, these proposed missions rely on zero propellant. Nothing. They deploy massive, ultra-thin metallic films, sometimes thousands of square meters across, and just let the actual physical pressure of photons pushing against the sail slowly, gradually tilt the spacecraft out of the flat plane over a long period of time.
But you know what? Mission designers now believe the ultimate breakout strategy is to actually combine both, spiraling in with a sail, executing a violent Oberth burn at perihelion, and then riding the sail up into the pristine polar regions. You genuinely get the best of both worlds here. The sail gracefully spirals the craft close to the sun without wasting any fuel. The violent Oberth burn provides that massive vertical kick, and then the sail carries the craft higher and higher into the totally unmapped territory above our star. Section 5. The view from above. What awaits us?
The whole effort to escape this sideways prison isn't just about showing off a cool astrodynamics theory, it's about the unbelievable rewards waiting for us once we reach the top. Ascending out of the dusty plane provides a crystal clear window to hunt for alien life, a fundamentally different radiation environment, and the first ever top-down view of our entire solar system. You see, our planetary plane is extremely dirty. It's filled with this haze of dust left over from billions of years of asteroid collisions, a haze you can actually see from Earth at sunset as the zodiacal light. A spacecraft rising vertically escapes this dust within months, offering an incredibly clean, dark vantage point that is absolutely perfect for detecting faint signals from exoplanets or studying the cosmic microwave background. Plus, it enters a smooth, fast solar wind stream flowing at 800 kilometers per second, entirely different from the turbulent plasma we experience down here near Earth's equator. And of course, you finally get to look down and see the planetary disk as it really is.
So as we wrap up this explainer on what I'd call the greatest missing photograph in space history, ask yourself, to finally break out of our 4.6 billion-year-old prison, which escape method would you actually bet on? Humanity has mapped distant worlds, but looking down at our own solar system from outside its plane is a vantage point no robot or human has ever achieved. It is a photograph just waiting to be taken. So, what do you think? Would you trust the slow, patient push of a solar sail or the dramatic, fiery slingshot of an Oberth dive? Keep that thought with you and stay curious about the frontiers we've yet to cross.